Hello, everybody. I hope all is well. Just wanted to take a look at an interesting side lecture on dark matter. I usually don't do lectures on physics like this, but I definitely want to start getting into it because it's definitely interesting. But I had a couple viewers that were interested in dark matter and the planets orbiting in the solar system, as well as the galaxies rotating. So we'll definitely take a look at dark matter. So let's look at this and wonder if dark matter actually exists today. All right, so first, let's take a look at a planet orbiting the sun. So we have planet here with a mass little m, with an orbital velocity of v. And then we have the sun, which big mass of m, and the distance between the two is r. So the planet orbits with an orbital velocity v here. So we can actually show through the centripetal force, which is the force keeping a planet in motion, is given by, we have right here, we got mv squared over r is equal to g capital M little m divided by r squared. So we can see that the two little m's on each side cancel. One of the r's cancels, and we're left with v squared equals gm over r. And in this case, gm is constant, the gravitational, universal gravitational constant, and the mass of the sun here. Those are both constants. So we can say that v squared, or the orbital velocity squared, is proportional to 1 over the distance r. So as r increases, v squared, as a consequence, must decrease. So the further a planet is away from the sun, the smaller the orbital speed becomes. So basically, in passing, we can just say that this is equivalent to Kepler's third law. So basically, when thinking about the time it takes for a planet to complete one revolution around the sun, that time t will be the distance the planet travels, which is 2 pi r, and that would be divided by the orbital speed v. So we know that v squared is equal to gm over r. So squaring the entire equation, we get t squared equals 4 pi squared r squared over v squared, which v squared is just gm over r. So then we're left with 4 pi squared r squared over divided by gm over r. And basically, we get this equation at the top here. So 4 pi squared r cubed over gm. And then we can basically say that 4 pi squared over gm is equal to a constant, since the gravitational constant and the mass does not change, and the value of pi does not change. And 4 is obviously inputted in there, and that doesn't change either. So 4 pi squared over gm is a constant. Therefore, we can say that t squared is proportional to r cubed. So basically, we say that the time it takes for the planet to make one revolution around the sun squared is proportional to the distance cubed. So let's just take a look at the v squared equals gm over r, and v squared is proportional to 1 over r. This is an important equation during this entire lecture. So the implications for this, for planets orbiting around the sun, which obviously this graph is not to scale. So the further you travel away from the sun, the lower your orbital velocity becomes. So we have Mercury right at the top here. We have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. So this would be the orbital velocity plotted against the distance r. So you can see Earth is right here. So we're about a third of the way down on the graph here. But interesting fact that we can apply this to would be, let's conduct a thinking experiment and consider what would occur if a planet were to orbit inside of the sun. And of course, this is not a practical rendition. Nevertheless, it is very interesting. So let's take a look at that. So we have a planet orbiting inside the sun here. So here's the sun. Here's a planet orbiting inside. So what governs the speed of the planet orbiting inside the sun? The answer is, of course, is that this formula, v squared equals gm over r, v squared proportional to 1 over r, still applies. G does not change. G is still the universal gravitational constant. However, the mass m becomes the only mass that will be relevant for a planet orbiting inside the sun, and that would be the mass enclosed within the planet's orbit. So these black lines here, just the mass in here. The mass outside of this, so the mass here, actually cancels out. Thus, a smaller mass arises within this equation. Once you get inside the sun, the graph plotted previously changes. So let's take a look at that. So as we can see, here's the graph that we plotted previously to the right of this dashed line. You can see the planets and their orbital velocities plotted against the distance away. And then from this dotted line down to the left would be inside the sun. So you can actually see that as the distance goes towards the center of the sun, the orbital velocity actually goes to 0. So if the orbit were exactly at the center of the sun, the orbital speed of the planet would be 0. So the pattern goes, as the further you are away from the sun, the slower your orbital speed will be. If a planet could orbit inside the sun, it would also have a lower orbital speed as you move closer to the center of the sun. This is, of course, not probable, but is crucial to the next piece of information. So let's take a look at a galaxy. So let's consider a galaxy of stars, and a star positioned somewhere in that galaxy with an orbital speed v. So we'll choose this star here, moving at an orbital speed v. So you might think that on the basis of what we just observed, if you were to plot the orbital speed of the star in question against the distance from the center of the galaxy, then you would see a graph that is as follows. So let's take a look at the theory. So basically, we should be seeing a graph like this on the basis of what we just observed. So this is exactly as the same, the previous graph. The further you travel out, as far as the star is concerned, the slower the orbital speed will be. If you travel very close to the center of the galaxy, the orbital speed will also decrease. That is what you would expect on the argument as we derive for the graph of the solar system. In fact, if you actually observe stars in a galaxy, what you find is that the velocity remains unchanged, no matter how far you travel out. And the graph is what you would expect from the formula we had derived earlier. So right here, so this graph here is what you would expect, but in reality, this is the graph that you get. So you have this little jump here in orbital velocity as far, and the further you go out, then it gets to a certain point where the velocity actually remains unchanged for the distance all the way out to the edges of the galaxy, which is definitely an interesting implication. So basically, this formula still applies. So we have v squared equals gm over r. So the velocities of stars are independent of the distance from the center of a galaxy. So what does that actually mean? So earlier we had derived the equation shown here, v squared equals gm over r. V squared is proportional to 1 over r. If the velocity squared is a constant, that means gm is a constant as well. That means that m over r must be a constant. So for this graph, which is shown here, what we are saying is that m over r is a constant in order for the orbital speed to be constant, which is very interesting. So what is m in this instance? M is the mass contained within the orbit of any given star. At first sight, you might think, well, that is perfectly easy to understand because obviously the further out in the galaxy you go, the more stars there are going to be within the orbit of a particular star. Therefore, the more mass there will be within the orbit of the star in question. So as radius increases, or in other words, the further you travel outward, the total mass within the orbit will increase because there are more stars within the orbit. Therefore, it is perfectly reasonable to support or to suppose that the mass contained within the orbit in question divided by the radius, the distance from the center of the galaxy, will remain constant. But, in fact, this does not explain it. If you travel to the edge of the galaxy, then as you move out to the furthest stars, the mass contained within that orbit barely changes at all. So we certainly expect, even if it were true for the inner stars, we would expect to where the other in respect to where the other stars are, where the amount of mass is hardly changing, you would expect the star's orbital speed to begin to slow down. But even at the edges of a galaxy, the orbital speeds are remaining the same. So you cannot account for this by assuming that the mass is increasing in proportion to the distance from the center of the galaxy. So, a serious problem arises from the graph that shows the orbital speeds remaining unchanged, so this here, because if that were true, if the orbital speed of the outer stars were as high as measured to be, those stars would not have enough centripetal force to maintain an orbit purely based upon the gravitational formula we derived. These stars should simply decouple and fly away into outer space, and it should not be possible for the galaxy to keep them in orbit because there is not enough gravitational force from the mass of the stars we observe. So we come to the conclusion that the mass of the galaxy must be greater than the observed mass appears to be based on the stars we observe in the galaxy. And there are ways of determining the mass of a galaxy based upon the observation of stars, but there is also a topic called gravitational lensing. This is a feature or phenomenon in general relativity. It states that if you take any object, or massive object, and you take a photon or particle of light that just skims the edge of that object, it will in fact be diverted, which I'll probably discuss that in more detail in another lecture. Had a few questions about that as well. But we can explain why this happens using Newtonian mechanics. You actually need to involve general relativity as well, but let's start off with Newtonian solutions. So, let's consider a massive object of radius r, capital R I should say, with a photon of light just skimming the edge and diverting through an angle of alpha. So we have v equals the speed of light for the photon coming in. Just barely skims the massive object here, and you might think that it would continue traveling on a straight path. However, it actually actually diverts at an angle of alpha. So we have a delta V in there, or a change in velocity. And then from this edge to this edge would be 2 times r, which is just the diameter of the object. So basically, this means that a photon traveling at the speed of light has been diverted with a velocity delta V in that direction. We can see that it has been diverted here within this direction. If the photon's velocity has been changed, there must have been it must have been subjected to an acceleration, and with Newtonian mechanics, we can identify that acceleration. So, in Newtonian mechanics, gravitational force F equals ma is also equal to g times m times little m over r squared. So the little m's cancel, which gives you an acceleration of gm over r squared. Now, a change in velocity is equal to the acceleration acceleration times the change in delta t. So the change in time, for practical purposes, the gravitational impact of the massive object is at its maximum as the photon travels a distance of 2r. So it's actually maximized in this region here. So this photon is traveling at the speed of light. So how long does it take to travel a distance of 2r? The time, delta t, would be 2r over c. Now we can say delta v is equal to gm over r squared, since the little mass cancels here, the little mass cancels here, so we're just left F equals gm over r squared. And we have delta t to r over c, so delta v would be gm over r squared from the force, times the time to r over c, and we get 2 mg over rc, which that's definitely an interesting little side there. So let's take a look at the vector diagram. So let's see here. So we have a side length of c. This is the photon of light coming in. This is delta v, which is 2mg over rc, and we have an angle of alpha. So if the angle alpha is a small angle, we can say that alpha Newtonian is equal to 2mg over rc squared. So alpha will be a small angle since g is a very small number and c squared is a very large number. So we have g on the numerator. So we have g in the numerator here, and we have c squared in the denominator. So g and c squared will combine to produce a very small angle for alpha. Thus, you need top-tier equipment to detect that angle. Alpha was derived using Newtonian mechanics, and that, in fact, you also need to use general relativity. If you use general relativity, amazingly enough, you find the solution, or the correct solution for alpha, which is the angle relativistic, is actually 4mg that we have right here. So we have 4mg over rc squared. And in a peculiar way, you find that the general relativity solution of alpha is just double the Newtonian solution. So the Newtonian solution here is 2mg over rc squared, and the relativistic solution is 4mg over rc squared. If you measure that angle, 4g over c squared, so we have 4 times g over c squared, so if we just take the m, take the r out, 4g over c squared is actually a constant, and you can observe the radius of an object in question. Thus, you can deduce that you can also deduce from this equation the actual total mass of the galaxy. The mass you deduce from this gravitational lensing is much greater than the mass you deduce if you attempt to work out the mass of a galaxy purely on the basis of the number of stars within that galaxy. And so we reach the conclusion that a galaxy must contain matter that we cannot observe. This matter cannot be accumulated in the middle, otherwise the orbital speeds of the outer stars would fall off as the distance from the center increases, just as planet orbital speeds fall off as the distance from the sun increases. Thus, the matter must be spread throughout the galaxy, possibly in the form of halos. And this is matter that we cannot see, and this is also known as dark matter. So, what is dark matter? Well, one argument states that dark matter actually does not exist. The problem actually lies within the concept of Newtonian mechanics. So, we can say that F is equal to G times M times little m over R squared. But what if the denominator actually isn't R squared? So, suppose it is almost R squared, but not quite. Suppose we have it assumed it is R squared for the practical purpose. It does work. Suppose R squared at large distances is not right. If that were the case, this would actually explain why stars and galaxies behave as they do, and this is called the modified version of Newtonian gravity, or that is termed MOND, so modified Newtonian dynamics. So it's definitely interesting. So F equals M times A interesting value of mu over A, or mu times A over A0. And then gravity, modification of gravity, becomes G times mu over G over A0. And if you work out the math, you find a new fundamental constant of A0 is 1 times 10 to the minus 10th meters per second squared. Which is definitely an interesting value here. And another argument states that the mass within galaxies that we cannot see is accounted for by neutrinos. There are billions upon billions of neutrinos being created inside stars at all times. Maybe these somehow coalesce to form some type of mass. The mass of a neutrino is not yet known, but it is assumed to be near zero, much smaller than an electron. If it has a mass, albeit very small, if you got billions upon billions of them, they could create a massive amounts of mass, if you will. And then there are those that believe that the additional mass could be machos. So there is a massive, these are massive compact halo objects. These could be black holes or brown dwarf stars. These stars are stars in which have depleted all of their energy and are no longer emitting light. Or maybe it could be that stars have coalesced to become another type of star, but did not quite have the energy or enough mass to form the first nuclear reactions to take place. Thus, they never became bright. Thus are scattered throughout the galaxy, adding to the mass, but not in a visible way. Another theory for dark matter is also called WIMPs. So WIMPs are weakly interacting massive particles. This assumes that there are particles that we have not yet detected that are supermassive particles, likely heavier than the Higgs boson, just never had enough energy. We just never had enough energy to detect them, which is very interesting. They would most likely have some unique properties, some interesting properties. That I'll have to go into another lecture because that would probably be an hour-long lecture for that one there. But interestingly enough, let's take a look at it. So, of all the matter in the universe, 83% is dark matter and 17% is the matter that we can see. And the more interesting idea that would explain dark matter is what is known as parallel universes in other dimensions. So in the theory of general relativity, there are additional dimensions, around 11 dimensions, and these are dimensions that we cannot see, observe, or understand. So this means that there's another universe within our universe in another dimension that we cannot see or reach. But there have been some experiments at CERN that have had some interesting implications. So if we consider our universe to be flat, there could be a parallel universe just above it, also with stars, and we cannot interact with it or see it or experience it other than its gravitational effect on our universe. So dark matter could be the addition of this gravitational effect. It's definitely interesting. Like I said, definitely check out the CERN's website. They have been doing some pretty interesting studies on other dimensions. They recently just reached 13.6 tera electron volts in beam 1 and beam 2 combining, which is very interesting. Seems like they could be opening another dimension or something along those lines. But there's also some other things that we have to consider as well. So people also talk about warm dark matter and cold dark matter. This has nothing to do with temperature, rather than relativistic versus non-relativistic particles. For galaxies and stars to form, you would need cold dark matter. Otherwise, particles would travel way too quickly. So on the left here is the warm dark matter. This is just a relativistic version of it. So you can see that there aren't very many particles here coalescing to create um, for the galaxy to form and stars to form because they're moving entirely too fast. On the right here, you can see cold dark matter. You can see more particles coalescing, creating stars, planets, galaxies, things of that nature. So basically, we have yet to discover what dark matter actually is. And finally, for those of you who've been asking, dark matter is not the same as dark energy. These are aspects. These are aspects that are entirely different and have yet to be discovered as well. Dark matter has been used to explain what we have been discussing here in this lecture. Dark energy has been used to say, although the universe is expanding, if the only long-term force acting on the universe were gravity, then the expansion would slow down. And as gravity begins to slow all the objects in our universe, but now the expansion is interesting. Interestingly enough, our universe is actually expanding. It's not actually slowing down, it's actually ever expanding. And if that's the case, there must be some sort of negative gravity at work, which is in the form of dark energy. It's a very interesting topic there. But, so dark energy, just as a conclusion here, is approximately 73% of the universe. Dark matter is 23% of our universe. And the matter that we can see, observe, experience, feel, things like that, are only 4% of the universe. So 96% of our universe actually remains a mystery. So there are tons of Nobel Prizes on the shelf for people that can discover exactly what this is. So we're definitely, here at World Weather Authority Studios, we're definitely doing some research and reading various articles, which we can post a few up. We'll definitely post a few on our Facebook page. But this video here will be available on Facebook and on YouTube as well. The music you guys heard in the beginning is again by Guitars and Ghosts. So I will definitely post that link to that channel in the description of this video. Definitely go check them out. But yeah, like I said, 96% of the universe remains a mystery. So it's definitely an interesting thought to think about that we only know about 4% of our universe. So it's definitely very interesting. But, alright guys, just wanted to thank you guys again for joining me in another lecture. This is definitely a side lecture to the ones that we've been doing on the atmosphere, but nevertheless, this is definitely an interesting lecture. If you'd like to see more about dark matter, dark energy, or topics in physics, definitely shoot us a message or definitely comment down in the video. Definitely be helpful. But alright guys, thanks again. Never stop chasing.